In this module, we'll be revisiting our one type of real number, that is your irrational numbers. Let us now re-revise it.
Revisiting irrational numbers. If a number x cannot be written in the form p by q, where p and q are integers and q is not equal to 0. For example, √2, √3, √5 are irrational numbers. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. Let us understand it with the help of an example. Prove that 3 plus 2√5 is irrational. Solution. Let us suppose 3 plus 2√5 is rational. It implies 3 plus 2√5 is equal to p by q in lowest form, where p and q are integers and q is not equal to 0. So it implies 2√5 is equal to p by q minus 3, or 2√5 is equal to p minus 3q by q, or √5 is equal to p minus 3q by 2q, where p and q are integers. It implies p minus 3q and 2q are integers. So, p minus 3q by 2q is a rational number, or √5 is a rational number, as √5 is equal to p minus 3q by 2q, which contradicts that √5 is an irrational number. Therefore, our assumption is wrong. Hence, 3 plus 2√5 is an irrational number.
Now we'll be going through our rational numbers and their decimal expansion. Let us now quickly revisit what these things are.
Revisiting rational numbers and their decimal expansions. Theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p by q, where p and q are co-primes and the prime factorization of q is of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. For example, first 7 by 8 is equal to 7 by 2 raised to the power 3 into 5 raised to the power 3 by 5 raised to the power 3 is equal to 7 into 125 by 8 into 125 is equal to 875 by 1000 is equal to 0.875. Second, 3 by 125 is equal to 3 by 5 raised to the power 3 into 2 raised to the power 3 by 2 raised to the power 3 is equal to 24 by 1000 is equal to 0.024. Third, 9 by 80, 9 by 2 raised to the power 4 into 5 into 5 raised to the power 3 by 5 raised to the power 3 is equal to 10125 by 10 raised to the power 4 is equal to 1.0125. Theorem. Let x is equal to p by q be a rational number, such that the prime factorization of q is not of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers. Then x has a decimal representation which is non-terminating repeating. For example, 1 by 3 is equal to 0.666 and so on. 7 by 6 is equal to 1.1666 and so on. Similarly, 1 by 7 is equal to 0.142857, 142857 and so on. Theorem. Let x is equal to p by q be a rational number, such that the prime factorization of q is of the form 2 raised to the power n into 5 raised to the power m, where n and m are non-negative integers, then x has decimal representation which terminates. For example, first 35 by 50 is equal to 5 into 7 by 5 raised to the power 2 into 2 is equal to 7 by 5 into 2. The denominator of this rational number has only 2 and 5 as prime factors. Hence, 35 by 50 has terminating decimal expansion. Second, 51 by 24. 51 by 24 is equal to 3 into 17 by 2 raised to the power 3 into 3 is equal to 17 by 2 raised to the power 3. Denominator of this rational number has only 2 prime factors. Hence, 51 by 24 is a terminating decimal.
Now we'll be going through the use of Euclid's division algorithm. The basic use is to find the HCF of two numbers.
Use of Euclid's division algorithms. Example: find the HCF of 1092 and 330 by using Euclid's division algorithm. Solution: to find this, we need to use the Euclid division lemma, and it states if a and b are two positive integers, then there exist two integers q and r such that a is equal to bq plus r, where r is greater than or equal to 0 and less than b. Now we apply this on the given two numbers and we get 1092 is equal to 330 into 3 plus 102. Now we need to check the value of r. If r is equal to 0, then b is the HCF of a. So in this case, r is 102. That is, r is not equal to 0. So that means 330 is not the HCF of 1092. What do we do now? We move to the second step. That is, we again apply the Euclid's division lemma for b and r. Now b is 330 and r is 102. So now we apply Euclid's division lemma and we get 330 is equal to 102 into 3 plus 24. Look at the value of r, and again r is not equal to 0, and the value of b is equal to 102. Now we apply Euclid's division lemma on b is equal to 102 and r is equal to 24. We get 102 is equal to 24 into 4 plus 6. Here value of b is equal to 24 and value of r is equal to 6. So again we use the Euclid's division lemma on b is equal to 24 and r is equal to 6, and we get 24 is equal to 6 into 4 plus 0. This time we get the value of r is equal to 0 and the value of divisor is 6. Therefore the HCF of 1092 and 330 is 6.
In this module, we'll be going through prime factorization of numbers. Let us now quickly go through this topic clearly.
Prime factorization of numbers. Example: complete the missing entries in the following factor tree. Solution: in this factor tree, we have 3 boxes filled with 2, 3 and 7 and 2 boxes are empty. Now we mark them as x and y, so we need to find these numbers. Now look at y. As y has 3 and 7 as factors, so y is equal to 3 into 7 or 21. Now look at x. As x has 2 and 21 as factors, so x is equal to 2 into 21 or 42. So the value of x and y is 21 and 42.
Now in this module we'll be going through the application of the concept that we had gone in our module 1, that is application of Euclid's division lemma. Let us now quickly understand it.
Application of Euclid's division lemma. Example: use the Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Solution: we first write the Euclid's division lemma as shown here. Now let us take any two positive integers, say a and b, and take the value of b as 3. We have taken b as 3 because in the question 3m or 3m plus 1 is given. Now a is equal to 3q plus r for some integer q is greater than or equal to 0. Now r is equal to 0, 1 or 2 because r is greater than or equal to 0 but less than 3. That means the remainder is either 0, 1 or 2. If we divide it by 3, then the remainder can never be 3. So a is equal to 3q or 3q plus 1 or 3q plus 2. Now let's take the square of it and we get a square is equal to 3q whole square, 3q plus 1 whole square and 3q plus 2 whole square. So a square becomes 9q square, 9q square plus 6q plus 1 and 9q square plus 12q plus 4. Let's simplify this further and we get this now. We can represent a square as 3k1, 3k2 plus 1 and 3k3 plus 1, where k1, k2 and k3 are some positive integers. So we can say that the square of any positive integer is either of the form 3m or 3m plus 1.
Now we have come to the end of our chapter. I hope that you are able to appreciate the concepts and what all you have learned in this chapter. You all will be able to do every question that is given in your textbook related to these concepts. Thank you.